Of this lecture, I'm going to talk about a new paper that I have with Richard Newell, and who's now at Duke University. He's a university fellow at RFF, and Louis Prionis, who was at RFF, and now he's at grad school at UC Berkeley. And so this is putting an application to the electricity sector, such as kind of like I was alluding to before. And it's based on the 2008 GEAM paper I was telling you about, but we've done a few things to update and explore these issues more deeply, in particular, the role of policy interactions. Okay. Now first, so I'll give a brief description of a paper that Louis and I did in the International Review of Environmental Resource Economics. Reviewing the literature on policy combinations. And just to make sure that you have a little bit of intuition of what goes on when you overlap policies. Let me see if I'm missing the slide on emissions trading. Okay, so there's actually a bit of a literature on what happens when you have a cap and trade system. So you fix the total amount of emissions, and then you overlap, say, renewable energy policies on this. Because this has been very, among economists, has been the EU sort of 20-20-20 policies are pretty controversial because, why are we forcing the market to do more renewables than it wants to? So like I mentioned before, once you put a cap on emissions, any other policy that you throw on top of it does nothing to further reduce emissions. Okay, so it's only going to distort the market. So if you don't have some other market failure, then it increases costs. But it also has some interesting effects, though. So you have a cap on emissions, say, and you start subsidizing renewable energy. Okay, so what does that do to the market? Let's think it through. So you're subsidizing renewable energy. So compared to what the market would do on its own, what happens? More renewables. And then, so what happens to the carbon price? Right, it goes down. So you have more renewables than you would otherwise. So if you don't change anything else in the rest of the market, then you'll have fewer emissions. Okay, because you'll be displacing other sources if the carbon price stays the same. So to meet your cap again, to rise back up to the cap, the carbon price is going to fall. And so who does that benefit? But in particular, so let's think of the electricity sector. So we've got coal, gas, and renewables. It benefits coal to the detriment of natural gas, because you're crowding out. You have more renewables, so you'll be crowding out overall fossil energy. But now costs have fallen disproportionately for coal because the carbon price has fallen, so they actually benefit. So Chris Boehringer and Knut Einar Rosendahl have a nice paper laying this out, that renewable energy policies end up benefiting your relatively dirty technology. And then if you have other externalities from that too, air quality and whatever, so you can actually have additional costs. Yeah? Right, it's because you're subsidizing renewable energy. So you're subsidizing some part of the electricity sector, so necessarily, costs are going to fall, you'll have less conservation, and the emissions price will fall. It will necessarily benefit coal to the detriment of natural gas. So if you, I don't want to spend too much time on this, but if you look at that paper, it's with very simple math, you can show that that has to be the case. It can be a little different. If you're paying for the renewable energy subsidy by taxing by taxing the non-renewables in different ways, that might have a slightly different effect. But if you're just subsidizing renewable energy, it has to be that you're expanding renewables and driving down the price of carbon. And the net effect is going to benefit coal to the detriment of natural gas. The other point is that if you're using a renewable portfolio standard, so where you have a market share target for renewable energy, this can have some funny consequences, because you can think of, say we have a 20%, we want 20% of our energy to be from renewables. If that's binding, that's equivalent to saying we want 80% of our energy to be from fossil fuels. Okay? So you're linking the fates of these two things. And so as a consequence, suppose then you have supplementary policies. Oh, we really love renewables, so let's subsidize them. Okay? So what does that do? If you have a renewable portfolio standard, or a renewable fuel standard, like we have in the US, and then you subsidize renewables on top of that, what do you think happens? We've got the renewable portfolio standard is implemented with in a tradable mechanism where you have a renewable energy credit. Okay, so this means the non-renewable guys have to buy credits from the renewable guys to meet this target. But now we're subsidizing renewable energy. So what does that do to the cost of a credit? Right. Makes it cheaper because they're getting the subsidy, so they don't, to get the same amount of renewables, you don't need to ask for as much credit because that supply is out there, it's being subsidized. So, and the system, who does that make it cheaper for? Yeah, the guys who are buying the credits, whoever has to buy the credits, okay? So it's actually, by subsidizing renewables, you're lowering the cost of the RPS system, okay? And actually making electricity cheaper, so then you have less conservation too. So you have an expansion of output. Because if the fossil guys don't have to pay as much of an additional tax, then they can produce more and overall demand is higher. So you actually increase emissions by subsidizing renewable energy when your binding policy is a renewable portfolio standard. Okay? So that's why it's important, when you're thinking about overlapping in policies, it's important to think about what kinds of policies you're overlapping. So we tend to make a distinction between fixed price policies. Maybe I can. So we can have fixed price policies. So that would be like a carbon tax or a fixed subsidy for abatement or renewables or something. And then we have endogenous price policies. And this would be your tradable mechanism, so like cap and trade or an RPS. So when you're thinking about overlapping policies with these endogenous price policies, then you have to realize what's going to happen. That you're not necessarily going to have an additive effect because the price in these is going to adjust. And so you can get some counterintuitive results, like renewable subsidies benefit the dirty guys or allow for more emissions in the case of an RPS. So that's the paper with Lewis. So again, here are lots of sort of, it's not sounding too good for subsidizing renewables. So again, why do we want overlapping policies? And this is what we have to come back to. It's an economic principle that we basically want as many policies as we have problems, and we don't want more. More than that actually raises costs, and less than that is inefficient. So if our only problem is greenhouse gas emissions, say, then greenhouse gas price should be sufficient for doing it. If renewable energy share is the only target, say for energy security reasons or whatever, then an RPS should be an efficient policy tool. But if there are other market failures, then we need target tools for them. So we already went through kind of a list of potential market failures. These are the two that we're going to focus on in this paper, or two in addition to the emission externality. So knowledge market failures. So again, this is our inability to fully appropriate the gains for the innovators. If you want a nice review article on this issue is Jaffe et al. In 2005. And we're going to think about spillovers as coming both from R&D and from learning by doing. Learning by doing, so R&D is basically you can invest in creating innovation. Learning by doing means as you produce more, use the renewable energy more, then you learn about it and it lowers costs. The other market failure that we're going to throw in here that we didn't have in the previous paper is an energy efficiency demand side failure. So that for some reason, there seems to be an apparent undervaluation of energy efficiency investments. Now this is a huge literature in itself and a bit controversial. There's a lot of anecdotal evidence that people seem to be, and companies, there are investments they could make with really short paybacks, but they don't seem to be making them. So we don't really know why in all cases. There are a lot of reasons in theory why this might be the case. Have you heard of any of them? So why might people not, buy a cost-effective, more energy efficient appliance? What are some of the reasons? Yeah, to know that it's cost effective, right. It takes a fair amount of mental effort to, they're getting better at, like in the US in the energy efficiency stickers, they'll say, average cost per year, and you can look at the difference between them. But yeah, there's a lot of information involved, and ultimately the differences, may not be that big. There are a lot of other things you need to worry about. Buying a car is a good example. Energy efficiency tends to be, number 10 feature that you're looking for. Bounded rationality. So there are those kind of issues. What about if you don't own the apartment that you're living in? So there's landlord-tenant issues. Who pays the bills versus who makes the decision about whether to insulate the building or buy the appliance. So reasons like these. And so there's a nice review article by Gillingham et al. From 2009. That sort of goes over a lot of this literature. And then in empirical literature, they're trying to tease out, well, what is like the effective rate of evaluation? That tends to be all over the map, but they're on some people find over, some people find under. On balance, it does seem to be undervaluation. So this is something we want to look at, but also play with, because we don't have a lot of good information as to what the extent of undervaluation is. But it can also affect, what your policy portfolio wants to look like. Okay, so the objectives in this paper is to think about how these multiple market failures, not only how policies interact, but also how these market failures interact with each other. And think about, to what extent does this justify some of the technology policies we've been seeing, so additional investment. Now again, we're just looking at these market failures, so I'm not saying that there aren't other things that could help explain why we're paying, 10, 100-fold the carbon price equivalent for renewable energy. But sort of the question is, plausibly, to what extent can knowledge spillovers and other market failures, explain or justify that? Okay, again, this is fairly, we try to keep the model fairly simple so we know what's going on in it. It's a partial equilibrium model of the electricity sector, so basically got a bunch of linear supply curves and a demand curve. So we have representative sectors that we divide into two types of technologies. So mature technologies, which don't really have significant innovation going on, or relatively less significant. And so that would be coal, natural gas, and then we have baseload technologies, nuclear and hydro, because those aren't changing a whole lot. And then we make a distinction then with innovating technologies, where we have sort of new renewables or non-hydro renewables, which in this paper we actually subdivide into what you can think of as conventional renewables. So this would be wind and other things like biomass that are fairly well established. And then advanced renewables like solar, where there's still a fair, they're higher up the learning curve, experience curve. And then we have two stages, because we need to think about the returns to innovation. So you can think of this as being a first stage, say like the next 5 years. So we have production of electricity, but then we also have accumulation of knowledge for renewables. And we do this both by investing in R&D and through learning by doing. So the more we produce with renewables in the first stage, then in the second stage, which is the knowledge application stage, the costs will be lower. So knowledge reduces costs in the second stage. And then we have, with this, so notionally you can think of our second stage as being from 2020 to 2035, with discounting in the second stage, that's roughly 10 years. So it's about twice as long as the first stage. In the second stage, to avoid complications in terms of the event, we want people to do the same thing within the stage, so we don't have discounting within the stage. But yeah. Okay, so we have knowledge accumulation for renewables. So specifically, we're going to have a knowledge stock that's a function of investment in R&D, which is H, and cumulative production, which is capital Q. And when we get into the numerical model, it's a very standard looking function like that. Let's see. And then the other important thing, though, so we want to model spillovers. And so we're going to model this as the benefits from cost reductions are going to be appropriated according to factor rho. So whenever rho is less than 1, then spillovers are present. Okay? Okay, a little more on the model. So we have the non-renewable sectors. So we're basically assuming this is a competitive market, but it ends up being, like linear supply curves in the model. So suppose these guys are profit maximizers. Their profits are going to be from the first stage, which lasts for N1 years, the price that they get for generation minus any tax they have to pay, less the cost of production, less any emissions taxes they have to pay. And then the same applies in the second stage. So emissions are basically going to be, we have two emitting sectors, and that's coal and gas. And total emissions are going to be the sum of their two emissions. So the mu being the emissions factor. And so the conditions for profit maximization then are they're going to produce up to the point where the price, market price of electricity equals the fully loaded marginal costs, so including the tax costs that they're paying. So what does this imply? There are a couple things that you can do with this. So if you totally differentiate this first order condition, you can see what's going on then as we play around with these tax variables or with the price. So the change in fossil fuel I and source I generation is going to be in proportion to the changes in those prices and inverse proportion to the slope of their marginal cost curve. Okay? So the flatter the marginal cost curve, the bigger the effect is going to be. The steeper the marginal cost curve, the less effect on quantity is a price change going to have. Okay, so I'll have a graph later just to picture that. And the other thing to notice here then is that, in equilibrium, the coal and marginal gas are produced up to the point where their marginal costs are equal, inclusive of the carbon price. Any fossil fuel, any tax that applies to both of them is going to wash out. So the only policy that differentiates between coal and natural gas is one that includes a carbon price. So that's going to be important to remember. So our representative renewable energy sector has a similar problem, except they also have, they want to invest in R&D. They may have a subsidy sigma for doing that. And the other thing is, okay, so let's first go to the second stage here, their first order conditions. So this is their, G is their cost of producing. So this is their marginal production cost in the second stage. They produce until the marginal cost equal the price plus whatever subsidy they're getting. Okay? Because that's the second stage. But in the first stage, producing also creates learning, which has a value by reducing costs in the second stage. So in the first stage, they actually want to produce beyond where marginal cost equals price plus subsidy. They want to go beyond that, and that cost is sort of like the investment cost in learning, to bring down, and that's the value of a marginal value of a cost reduction through learning in the second stage. Okay. Now the way we throw in spillovers here is this appropriation rate rho. Okay, so they value those second stage cost reductions by share rho. So when rho is less than 1, there's spillovers. And then we have a similar equation here for R&D. They invest in R&D until the marginal cost of R&D equals the marginal value of R&D induced cost reductions in the second stage, discounted back to the first, and evaluated at the appropriation rate here. Yeah, any questions? So that's basically how the model works on the supply side. And that's also what was going on in the Jean paper version. Now the extensions we added here is we have a few more supply. We allow nuclear to vary in this. Now in this paper we're distinguishing between wind and solar. But I think the bigger one is also that we have this question of energy efficiency investments and valuation rates. Okay, so this made the modeling the demand side for electricity a lot more complicated. So now we have to recognize that consumers, they're not buying electricity for the sake of it, because they like electricity as a product. They're buying it because they like energy services that they get from electricity. And so if you invest in more energy efficient, energy using appliances, say, you get more services per unit of electricity. So you have to change a little bit how you're modeling demand for electricity. So consumers have utility from electricity services, and they can invest in improving this service to electricity rate. And then they may have subsidies for these investments, subsidies B for these investments in energy efficiency. And then they also have so we allow them to make both short run and long run investments. So short run would be within each stage, and you can think of that as like appliances. Long run, so there may also be investments that you make in the first stage that also carry over in the second stage, like insulating your house, some like long-lived assets. And then we allow consumers to have, it's a lot like the appropriation rate for R&D. In this case, it's a valuation rate for energy efficiency investments, so beta. So when beta is less than 1, we have undervaluation relative to what seems efficient. And again, it shows up in the first order conditions. But it won't show up in the utility function itself in welfare, because that depends on the actual, realized gains. It's just when you're making this decision based on your first order condition of how much to invest, you're undervaluing, adding an extra discount to what happens in the future. Okay, so that's important to recognize. It's something that affects decisions, but it's not the welfare calculations, because ultimately, when they realize that, they do care about how much they're spending the utility they're getting in the second stage. It doesn't get discounted for welfare purposes. Okay, but this basically, condenses it down into a constant elasticity demand function. And then so demand then ends up being a function of the price, the rate of electricity consumption per unit of services, which is itself a function of all these energy efficiency investments that you're making. And then this very short run elasticity, epsilon. And then you'll see when we go to, I'll talk about the parameterization in a bit. So then our net benefits from any policy changes depend on how these different categories change. So we'll have consumer surplus, producer surplus, government transfers, because we've got tax and subsidies policies, so we've got to keep track of that, and environmental benefits. So that altogether, those are the net benefits. What we're going to do in the simulations is we're going to hold the environmental benefits equal and have everything, all our policy combinations are always going to target the same emissions reductions. So it'll be kind of like combining a cap and trade program with this other stuff. So it's a bit of a cost effectiveness analysis. Just a little bit of math here. So you take the welfare expression, totally differentiate it. So you see how everything changes with a change in some policy parameter. Then you put in your first order condition, so you know how people are deciding, so you know certain relationships in some of these partials, so you can make substitutions. And then add in the fact that you know that the emissions price is going to adjust such that the same emissions target is going to be made. Then you kind of ask yourself, okay, so what would some policy portfolio change? How does that change welfare? And so you can decompose the change in welfare into these categories. So we see the first part here, you have a welfare change depending on how energy efficiency investments change. And the question is, so how are they valued? Well, and you notice that say for example, something that increases short-run energy efficiency investments in the first stage has a positive value on the margin to the extent that undervaluation, so 1 minus beta, is bigger than the subsidy for energy efficiency investments. Okay, so on the margin, a policy mix change that increases energy efficiency investment is going to have a positive impact on welfare if the subsidies undercorrect for the undervaluation. Okay, does that make sense? The next line here, this is the change in learning. So anything that increases first stage renewable energy output is going to increase welfare if the undervalued portion of the cost reductions, the undervalued value of cost reductions is greater than the subsidy for renewable energy. Okay. On the flip side, if that subsidy is too big and overcorrects for the spillovers, then anything that increases renewable energy is going to decrease welfare. Okay. So here you have something similar for R&D. a policy mix that increases R&D investment, increases welfare to the extent that spillovers are not corrected for. And then finally down here we have some other things that affect costs. So for example, if you have additional tax on fossil energy, things that increase fossil energy are going to impose additional costs. And here in the second stage, if you're subsidizing renewable energy, things that increase renewable energy tend to lower welfare. Here you increase welfare if you're taxing. Now this is going to be, this makes sense if you think about, well, what is the optimal policy combinations? You want to correct for all your externalities. So we already have the emissions price in there. So if we set the R&D subsidy equal to the spillover rate, the learning subsidy equal to the value of learning spillovers, and all of the energy efficiency subsidies equal to the undervaluation rate, then and all of these additional taxes and subsidies are zero, then that's the optimum. Your marginal change in welfare is zero from a small policy change to that point, because you're up at your optimum. So you don't want additional taxes on fossil energy if you've got all this other stuff accounted for. So if you do have a tax and you're under providing fossil energy in some sense, and so that's where you get a small welfare. You can get a welfare gain by increasing fossil energy in that case. And since you don't have a third stage with learning, there's no extra benefit from production, renewable energy production in the second stage. So the subsidy in the second stage tends to reduce welfare on the margin. Okay, so this is sort of the intuition that's going to be underlying the numerical results we're going to see. Okay, so basically we take this model, we assume linear supply curves and linear marginal cost curves, and then we calibrate this to the Energy Information Agency's 2013 Annual Energy Outlook. And then we have knowledge functions that we calibrate basically the same way we did in our GENE paper, which is using available data from empirical R&D and learning literature. Although I'll say that that's there's still, the very small literature that's very specific to renewable energy policies, renewable energy technologies in terms of understanding their spillover rates and stuff. So that's something that we want to play with. And then on the demand side, what's important to understand is there's empirical estimates out there of what kind of very short run, short, medium, and long run elasticities are. And so we sort of know how people are behaving. We take those estimates and then we use that to calibrate the energy efficiency cost functions. So what's important to know there is that we're going to be a little bit agnostic. We don't really know what the undervaluation rate is, but we do observe how people behave in terms of their responses to price changes over time. Okay, so we're always going to target these same elasticities, but then our assumption about what that undervaluation rate is then going to change how we calibrate the costs of energy efficiency investments. Okay. So what does this look like in the baseline? So this is basically the AEO baseline, which we've condensed into two stages. This is the US, so you see that we've got a lot of coal and natural gas, nuclear. So renewables are actually a pretty small share of the market, less than 10%. Although there is a pretty significant cost reduction going on. So here, so for example, up in the upper left-hand corner is solar. So these are what the supply curves look like, and the first stage is the solid, and the second stage is the dashed line. So solar is the light blue up in the corner there, and then it's very steep and small, and it pushes out. So there's actually close to a 30% cost reduction in the baseline for solar and 7% for wind. And then you can see kind of what else is going on. So remember your quantity response to a price change is bigger the flatter the curve. So this is coal here, it's very flat. And then natural gas is green. So in this case, if expanding renewable energy, changes tend to crowd out more coal than gas in this model. Okay. So what are some of the results? So here, let's just break this down. So in these columns here we have, suppose we just rely on emissions price by itself, okay, knowing that we have these other market failures. So what are the costs and what does the policy outcome look like? So we're going to target a 40% emissions reduction in the electricity market. So this is more ambitious than like the 20%, say, in the EU, but it's sort of recognizing that disproportionate emissions reductions come from the electricity sector. And so we see that this generates a price of about $14 in the first stage and $35 in the second stage. Oh, why am I missing the renewable energy? Okay. Well, okay, looking at the welfare costs then, so we do two things. So one is assuming that there's no undervaluation of energy efficiency. And then we look at, well, what happens when you add in a market failure there, say a 10% undervaluation. And what this does is it doesn't really affect the responses, but it does affect our calculation of welfare. So remember, we're observing how people respond. So that doesn't affect how people respond to the price changes, but it affects our calibration of the costs. So with the 10% energy efficiency undervaluation, the emissions price policy has a lower cost because you're getting extra benefits from inducing more conservation that was already undervalued. So then we look at, so what is the optimal policy combination? Well, with no energy efficiency market failures, we just have the knowledge spillovers. And so it's easy, with 50% spillovers, it's easy to calculate the optimal R&D subsidy is 50%. So I think the value in this model is that it's a lot harder to calculate what the optimal learning subsidy is. It's not 50%. Because again, you already have incentives to produce with renewable energy. So the question is that value, the value of learning is how much you're bringing down the cost in the second stage. Okay, and the question is, so how much does an additional kilowatt hour in the first stage bring down costs in the second stage? Well, it turns out that the optimal subsidy for learning is quite small. So it's less than $0.01 per kilowatt hour for wind, and it's about 5 cents for solar. So that's quite modest. And then if you add in a 10% energy efficiency undervaluation, what does that do? That lowers your optimal subsidy for learning, because subsidizing renewable energy tends to lower costs, like we were saying before. It lowers electricity costs, and so then you get less conservation, which is undervalued. Okay, so what you do, instead you have a 10% subsidy for energy efficiency investments to counteract that market failure, and then also you're getting more of your reductions from the demand side, so you just don't need as much from renewables. So those optimal subsidies go down a little bit. I mean, it's not huge, but. And so then we look at, so how much does the optimal portfolio improve things relative to the emissions price alone? And it's 16% and when you just have the knowledge market failures, and 25% when you also have the energy efficiency undervaluation. So that's sort of the kick that you get from the optimal portfolio relative to only the carbon price alone strategy. And it's actually, you know, it's significant, but it's actually fairly modest. And we're going to see that the costs of getting your policy, your combination policy wrong can actually far outweigh this, this benefit. Okay, so we do, but okay, we're running out of time, but but it was sort of an important question. It was a surprise to me just how low the optimal subsidies for renewables was. I mean, especially if you compare that to what we're actually paying for renewable energy, it's really small. So 5 cents a kilowatt hour for solar. And so the question is, so what is this sensitive to? Because there are a lot of things we've sort of had to, you know, make assumptions about in this model. So one thing is, okay, the reduction target. So we were looking at 40%. If you ramp it up, yeah, so the optimal subsidies go up a bit, particularly for solar, it goes up to, you know, over 6 cents a kilowatt hour. But that's still not that big. But what really goes up, this is the right-hand axis, is the emissions price. So as your target gets more stringent, it becomes a lot more important to get your emissions price right and high than, you know, fiddling with the renewable energy subsidies. They're not that sensitive. So what about knowledge spillovers? Obviously, that's part of the value of this. So as we increase the spillover rate, we do see that the optimal subsidies get higher, particularly for solar. The thing is, you know, it's really hard to get it above 1 cent for wind. And your optimal emission tax goes down because then you know, you're correcting for the knowledge market failure, you're getting more innovation and more renewables, so you don't need as much push from the emissions price. What's interesting though is the sensitivity to energy efficiency undervaluation. So like I said, subsidizing renewables tends to drive down electricity prices, and that exacerbates the energy efficiency market failure. So this, if you're not correcting it, then you see that, or are we correcting for it? It must be that we're correcting for it. So because the emissions price is really going down, so just by correcting for the energy efficiency market failure, you're getting some pretty substantial reductions. So for a big undervaluation, correcting that means you don't have to rely on the emissions price anymore. You're getting so much just by correcting that market failure. And then you also don't need to rely so much on renewables. What's kind of interesting is we sort of explored, well, what's, you know, going on here? Why is learning, subsidizing learning, not that valuable? One thing is, in our baseline assumption, it seems that, you know, correcting the R&D externality seems to have a lot bigger effect than correcting the learning externality. So we do some other sensitivity analysis to play around with this. So lengthening the second stage, what aspect of the costs are being reduced, making learning more important. And so we see for wind, so this is sort of expressing it a little bit differently. So we're looking at the optimal, so what does our portfolio of technology policy spending look like? How much do we want on R&D? How much do we want on learning? And how big is that relative to the revenues that we're getting from renewable energy generation? And so we see in our reference case, we want to spend about 2/3 of our portfolio on R&D. And the total spending is a little less than 20% of the revenues that wind is generating. So this, trying to get a sense of what, you know, what's the magnitude of these policies. And you can play around with that. And the only one that, so here we've really rigged it so that learning is a lot more productive and has bigger spillovers. So then you want to spend more on learning. But in the other types of scenarios aren't that reactive. Solar, on the other hand, there seems to be a lot more value in learning. It's higher up the experience curve. It has more to go. And the total spending equals close to 100%, you know, 70 to 100% of the revenues. Okay. So we're pretty much out of time and we have a seminar. So I will just leave you with the fact that we also did this for calibrated this for the EU and looked at the cost of, so we have a baseline scenario which just has the cap and trade system, the ETS. And then we looked at what is the cost of overlapping the 2020 targets with that. And this is the cost of, this is called the reference scenario, the cost. What is the benefit of an optimal policy combination? Very small. Yeah, it's beneficial, really small. And then, so what was the cost of the cap? So if we got rid of the cap, what would the social gains be from that? We're not valuing the emissions side. So what is the cost, the policy cost? And so basically, imposing the 2020 targets on top of the ETS doubles the cost of the cap and trade system. So that's an example of, yes, so there are rationales for technology policy, even as a complement to emissions pricing, because there certainly are other market failures to worry about. The question is realistically, how big are those? And at least looking at knowledge market failures, it seems to be fairly modest. And getting the policies wrong can actually be pretty costly.